Okay, so thank you guys for inviting me. I am just off of a flight from Toronto, so hopefully that means I'll talk as slowly as I should be talking when I give a talk. And then, so the slides here, I'm presenting a paper with Luca Ciambelli. I think he was here recently, and then Lisa Tabor was a master's student. I can try to keep track of time enough to respect the 30 plus 30. But I also think that this is a nice talk to be giving at a workshop style thing, because I feel like there's a lot of debate around the notion of radiation holography. And depending on the audience, I would say that most of what I would say would probably go through without as much debate if I said asymptotic radiation in holography. But I feel like for this audience, maybe we're on the side of we want radiation to be asymptotic. So, okay. First of all, let's go through the motivation. So the first thing is we want a holographic description of quantum gravity, because I guess it's the one thing that we've kind of distilled from string theory or Hawking's formulation. We're looking for some lower dimensional theory, hopefully without gravity, that can describe the same physics. And that's cool just because, again, two weirdly different descriptions of the same thing is also connecting different branches of mathematics. So that's fun. Celestial holography, a lot of people here know, or people who study Carrollian holography would also, I'd say, be studying the same thing, which is we want to really understand how to extend the holographic principle that we kind of believe in for asymptotically ADS spacetimes to flat spacetimes. And so the goal of this talk is to try to talk about a definition of radiation in ADS spacetimes that's going to let me take the flat limit and talk about the radiation that I'm used to in celestial. C'est bon? Okay, so but I can talk the same and you're going to make me louder? Okay, good. Okay, great. We can continue. Okay, so what am I actually going to try to do in this talk? First thing I'm going to try to do is basically the way that this paper was structured is we're kind of combining different people's results in ways that they might not consent to combining them and have fun, and we can debate about them throughout. So basically, Sinovia and Fernandez-Alvarez have this definition of radiation in de Sitter, and they also understand the flat limit of that. And we're going to try to do the naive thing and take it over to the ADS case, in which case there's this analog of the superpointing vector, which various people complain about the fact that the boundary is now in a space-like direction. But basically the point is that this definition of asymptotic radiation is going to be some commutator of the boundary Cotton-York tensor and the boundary stress tensor, where the stress tensor is the one we'd be used to in normal ADS CFT. So that's the first thing. And then the next thing is we're going to use a result by, I guess, Romain and Adrian, where you guys have basically understood Lambda-BMS story. And we're going to be able to connect this ADS guy to the flat limit to talk about celestial stuff. But in the meantime, I guess one thing we're going to try to talk about is the extent to which when you would normally talk about the asymptotic symmetry group in ADS CFT, you would have kind of like this class of metrics would break it. Now, the Lambda-BMS story also understands that as basically you want to preserve that class of metrics, and so you have a BMS symmetry in ADS or in de Sitter. But kind of there's a couple of things that are going to be interesting to see when you look at the ADS analog as compared to the flat case, which is kind of how you're changing the boundary metric in something that is kind of perturbative in lambda. And so is that a thing you would normally want to do in ADS CFT? Some people would say, not really. Other people would say it's fine if it's viewed as a source. And then the second thing is, I guess from the point of view of this flat hologram, it's nice to be able to see how these different boundary conditions, and it was already in the Lambda-BMS paper, reproduce the constraint equations that I need kind of as the starting point of these celestial symmetries that I'm used to. So those are a couple of things that I want to latch on to when we talk. But again, I'm going to be starting with the Sinovia result moving over. So this is outline of the paper and the talk, and we can stop at any point when we need to just break for our discussions if we need to. But basically, it's going to go ADS to flat, and then to like celestial holography in particular at the end of that. And so let's start. Yes. So one thing that I want to caveat, which maybe is less important for this audience, but I know whenever I run into people who do standard ADS CFT, I think part of the issue with what I would call radiation in this talk, they would want to call asymptotic radiation or something kind of modifying it, because depending on who you are, you might be fine with basically any sort of gravitational excitation bouncing off the wall of your ADS for your ADS CFT. And so I think that it's fair to say that roughly what I'm doing is a different order of limits. And so by looking at the asymptotic expansion of my metric near the conformal boundary, I'm basically not going to take L to infinity first. And in that situation, I really care about trying to map the conformal boundary of my ADS CFT story to the one I need in flat, where I have radiation that's going to be fluxing through the conformal boundary. I need those leaky boundary conditions. Versus a lot of people who would study the reflective boundary conditions would be more interested in just making sure that if I talk about the physics in a small causal diamond around the bulk point, that has some notion of gravitational excitations fluxing through, say, that boundary A. And so, for example, there have been other cool papers trying to connect the celestial symmetry story to ADS CFT, which I think are looking at this bulk point picture. And so they're not changing the boundary conditions, I think, for their ADS guys, but they're able to roughly use just the structure of what a 3D stress tensor and its shadow would look like in OPE with other operators near the same, say, like cut on the time coordinate there on the cylinder to make a statement that looks like a soft theorem and stuff like that. So they're able to do things with just the ADS CFT story, not changing boundary conditions, because they only care kind of about reproducing the right physics in that smaller causal diamond. And so I think kind of the motivation for this talk is more along the lines of, can I make sure that I understand like what I need to do in the ADS side to have the conformal boundary mapped to the one I would need in the flat case with radiation there. And then also, I guess there's some things to be said about if an ADS CFT, I need to be able to like have leaky boundary conditions in order to have my black holes evaporate. Like, I think it's not clear that you should just kind of ignore the need to have leaky boundary conditions if you actually want to do some interesting ADS CFT physics or talk about like black hole evaporation. But that's my little caveat and or thing to keep in mind, like where we are setting. We're trying to look, I think, at the conformal boundary in this thing. So, yeah. Yeah.
So A, maybe.
Mm-hmm.
How would you characterize?
Yeah, so I think the thing that I want to keep in mind is that the Lambda-BMS people have given me, for a fixed value of the cosmological constant, both the Bondi analog gauge expansion of like the data near the conformal boundary if I try to then like propagate it inwards, and also so what that would look like in Pfefferman Graham gauge. So my impression is that like going all the way to A would be like looking at R equals L, and that's not going to be what I'm seeing when I do consecutive limits. So I think that like what I'm trying to basically say is that I think it makes sense to have these like Lambda-BMS gauge guys and view it as like I have a singular kind of in lambda component of like a Pfefferman Graham stress tensor. And so we can see that later. But what I'm roughly saying is that I care about making sure that there is radiation at B. And some people would try to say that I never need it. So, okay. Yeah. No. So, and I think that's fair. So what I'm saying is that I'll have an equation that will say that maybe the standard way of viewing this is that the conformal isometries are the isometries of the background being whatever, like, so if the conformal class is like conformally flat, then there are more isometries of that class. But I think that most people would say they understand, I guess, how to like add sources. And the question maybe that I don't appreciate well enough is to what extent if I try to really deform the background and have a CFT on some non-trivial background, if I really need to have like I think the way that I view it is like if I wanted to look at like some finite number of stress tensor correlators, I would add a source and then I would basically vary with respect to it and then set it to 0 at the end. But I think in principle, it's fine to not do that step. But all I'm going to basically do is just say, oh, look, if I have this conformal class of metrics and it happens to be this particular one, then the set of diffeomorphisms that preserve that class is going to be larger, in general. That's all I'm saying. And then, but the neat thing, so the thing I want to contrast that with is that within the flat case is roughly the radiation is sub-leading as compared to kind of the leading structure. And so you get all of BMS, no matter what background you're on. So I think that's different, even if it's not precluding saying you do ADS CFT. And I think that's a fair point. I think everybody on the ADS CFT side would say the same thing you say. So like, let's take that. Okay, so the setup that I'm in right now is just solving Einstein's equations with non-zero cosmological constant, in particular, the right sign for ADS, so negative. And so then the standard procedure would be to go to a Pfefferman-Graham gauge. And so we're setting the radial components to specified values, and then the boundary metric is some conformal class of metrics, which a priori can be just one of your two sets of free data. And then the second free data is this pi 0, which is, I guess you can see the order in R here. And in Pfefferman-Graham gauge, it obeys what looks like a conservation law for this traceless symmetric rank 2 tensor. And so then on a couple slides later, I'll talk about, I guess, the definition of what one might naturally call like the asymptotic symmetry group. But the first thing is preserving Pfefferman-Graham gauge already restricts you down to a different subset of diffeomorphisms. And later we'll restrict it further if we want to talk about actually preserving the representative formal class. Okay, so for the next thing that we're going to need is the cotton tensor. And so I guess maybe for this audience, it might be more familiar than I am with it. But we have this geometry we're interested in, some CFT. We're interested in like kind of the conformal structure of that. And so a natural object would normally be the Weil tensor in higher D, and in 3D, that role is played by the cotton tensor, which is defined as follows in terms of the Schouten tensor and Ricci or whatnot. And so basically in our context, it's natural to look at the two-component guy, which is Hodge dualized, and our definition of radiation is going to involve this cotton tensor. There. So there's some identities that are useful to trying to kind of make it look a bit like the stress tensor that comes from Pfefferman-Graham gauge, and that is that it's automatically going to be symmetric and conserved just as an identity. So that is neat, and it transforms covariantly under conformal rescalings. And so in particular, basically, the notion of being asymptotically globally or locally ADS is sometimes used to talk about whether or not this cotton tensor is vanishing or not. So now let's go to Synovia's result. And this is just reviewing like the ingredients of it that we're going to take and then try to import to the ADS analog. And he would be doing this in de Sitter normally. And so what we're going to basically be doing is taking this Bell-Robinson tensor, which is defined in terms of the Bell tensor, and then rescaling it so that it doesn't vanish when you take R to infinity. And then those authors define this superpointing vector in terms of that Bell-Robinson tensor appropriately rescaled and the normal vector. And so in particular, it's conserved on the boundary. And what we're basically going to do is just take this all over to ADS. But a couple of things I guess are worth noting is that in the context of de Sitter, the proposal for no gravitational radiation was tied to the vanishing of the components tangent to the conformal boundary. And so we're going to propose the same condition for our ADS spacetimes and see what that gives us. And so roughly speaking, what we're doing is we're just extrapolating, in this case, not literally extrapolate CFT, but taking lambda to the sign that we want it to be, this proposal of Synovia to these ADS spacetimes, because most of those quantities still exist in ADS or de Sitter. The only issue is like whether certain vectors are time-like or space-like. And so there's a couple of things that are sanity checks for that, because again, like that was a very like mathematical result, and we're just doing the naive thing here. So the first thing is that basically in these spacetimes, we can check the flat limit is consistent. And then also there are some interesting exact bulk solutions where we know that there should be a non-trivial cotton tensor and an interpretation of radiation there, so it captures that. Yeah. Yeah, so I was skeptical of this too, right? Asking Luca, and then Luca checked with, well, I think when we sent the draft around and it was confirmed. So first of all, I don't think they were interested in ADS context. That's the first thing. But the second thing is also he had some misgivings about just being able to define the same quantities in the context where now the normal vector is not time-like, because he was worried about like the nature of the Poynting vector also being interpreted as time-like for him, if he wants to interpret it as like an energy flux. So no, this, I've already break it down to 3. So like, yeah. Yeah, so I made a little fast. So every time I have a mu index, it's going to be the full 4D. And then like little a would be 3D, and capital letters will be for the sphere. And I'm going to stick in 4 bulk dimensions throughout because that's where I have this cotton tensor in I story. So p squared should go null in the flat limit. And so most of the things where my sanity checks are in the flat limit. And there it has the properties that I would expect where it's like time-like, and I can also check the sign of the radial component, and assuming it's null, it checks out, which I'll get to, I guess, in a couple of slides. It will be there. It will be after I introduce the Lambda-BMS story. But in particular, the thing that happens is that this definition of radiation in the de Sitter case requires you to have both excited the stress tensor and the cotton tensor. And so the reflective boundary condition story would basically be like setting the cotton tensor to 0. And so effectively, like this definition of radiation, if I import it to the ADS context, would be calling anything with these reflective boundary conditions like a 0 radiation spacetime. So that's one thing where, depending on what you want to call radiation, you might have misgivings, but it is kind of nice that these two kind of nice geometrical objects are appearing in this definition. So this is a caveat, I guess, about how one might try to, say, define your conformal isometries. And so if, besides preserving Pfefferman-Graham gauge, we wanted to basically preserve the conformal class of that boundary metric, if the metric is conformally flat, you're going to have SO2, 3, and generically otherwise, if there's any like time dependence or other like non-trivial boundary metric, you would have a smaller conformal isometry group for this definition of what I mean by conformal isometries. Now the Lambda-BMS story is going to roughly not ask to do exactly this, but to preserve their class of kind of Lambda-BMS geometries. And so that's where they have the BMS group there. But it is, I guess, worth pointing out that depending on how you want to view the non-trivial cotton tensor as basically the background on which you're doing something, you wouldn't have like the CFT isometries for like a non-trivial conformal class of metrics. I don't think most people who do ADA-CFT see that as a problem, though. So this is the main thing for us is that it's different than in the flat case. Okay, so the thing to keep in mind is that cotton is really diagnosing the fact that you are in a different or non-trivial conformal class of metrics. So you can show that it goes both ways, that when this cotton tensor is 0, you have the maximum number of conformal isometries. And when it's non-zero, because it's basically it's defined geometrically in terms of the boundary metric, non-trivial boundary metric is gonna turn on the cotton. And so the fun thing that's gonna happen later is we're gonna see that the definition of radiation that we have here with this cotton and stress tensor will in the flat limit reproduce what we would expect for the definition of radiation. Yeah. Yeah. So that's, I would say that given what I've heard both things. So what I'm saying is that strictly speaking, to the extent that like the formal field theory should like be the background's conformal isometries, and I would say it's not a conformal field theory. But others would say, well, I'm adding a source and I understand how to do that to my CFT, and then if I do, then I'm fine, right? So maybe they'd say ADS-CFT follows through, but it's a conformal theory on a different background, and then they are fine with that. So, but I'm happy to hear both sides of it so I can fight back because I can only like agree with them right now. Yeah. 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 So I'll write down the metric in, I guess, both Pfefferman-Graham gauge and Lambda-BMS or Bondi gauge, thanks to these guys. And you will see that this is literally the radiation is like a time dependence to the boundary metric. So it's like literally the same like R squared term of the metric. Okay. Mm. Mm.
Deformation of the geometry to the timeline. That's what you call rules.
And this is why it's great for this debate. Like, and the cool thing, yeah. So definitely. Yeah.
So the hope is that you still have a holographic correspondence to a dynamical shear.
Yeah. No. It's in that direction. Now, the one question I'd try to throw back at you, because I do want to actually understand better, like how when they just say they're adding sources or doing something on non-trivial background, that's the same as what we want, because that non-trivial background is literally the radiation profile for me. And so I would normally in flat space think of that as dynamical, and I don't know if there's a problem that you run into with that. Yeah, I know, but I would love to hear. If you have more to say than I see, I'd love that, because I think I definitely see where, okay, I can add sources and that's fine, but I don't know if there's anything funny, because I need that to be my graviton. Yeah. Did you have a question or? Yeah. Okay, good, awesome. Okay, so I think this slide is basically flat. Yay. Now I know flat better. Maybe not well enough, but yay. Okay, we made it through ADS. I'm happy. So now we're going to talk about the asymptotic structure of asymptotically flat spacetimes, and that's where flat holography becomes fun, because you have this BMS group. So, like, I guess the second picture in my talk is just this Penrose diagram. Hopefully, we all know it. I am going to be looking at Bondi gauge for a lot now going forward, thanks to also the Lambda-BMS story, where I can go back to my ADS and Bondi gauge. So this is just setting up notation. Hopefully people here are familiar enough with it that this slide can be fast too. Okay, so now I want to solve Einstein's equations with no cosmological constant, and in particular, things that are important for my celestial story are these constraint equations, because basically they turn into the word identities that kind of started this whole story of seeing BMS actions near, say, future or past null infinity as something that you can match and then see that in scattering. But now the thing is that for this full class of metrics, with non-trivial radiation, whatever that is, you have the BMS group, right? And depending on who you are, you might have a different superrotation part of it. But unlike the previous case, it's like even if I have radiation, we're going to have BMS. And the second thing that I want to have before I start talking about matching the flat limit of the ADS story is what I would define as radiation in the flat limit. And so here, Sinavia's definition of radiation in the strictly flat guy is slightly different, because it's the full P mu, not just PA, at the conformal boundary being 0. And then you get, I guess, 3 types of equations for this 4D bulk. Like the U and R components are scalars, and then you have PA there. But basically together they would imply that you want du of NAB to be 0, and you want dc of NCA to be 0. And so as much as I'm saying that implies that the news is 0, it's actually slightly cuter. Basically those 2 conditions would leave for you any supertranslation or superrotation vacuum, because on the one hand, say the supertranslations and superrotations are both like the news is either constant or it's zero. And then the ones for which, so the news is zero for the super translations, and I guess there's an extra, like, I guess some magnetic component being zero or whatnot to get the form of the super translations. But for the ones that are holomorphic super rotations, even though you have a non-trivial news, that divergence would be zero away from where there were punctures. So let's basically, besides NVAC, it's basically saying there's no other news. So that's nice, and we're going to see that these same equations above are going to be reproduced in the flat limit of the previous one once we plug in Lambda-BMS gauge. So the point of a lot of work by Romain and Compare and Adrian is to find that you can do the same kind of Bondi-like gauge fixing for solutions with non-trivial cosmological constant. And there in particular, you find that when you go to the conformal boundary and you strip off the right number conformal factor, you now have a geometry that is time-like, like you'd expect when lambda is non-zero, and that cosmological constant sets the speed of light in the Carrollian limit. So the thing that is different about the flat limit, I guess crucially, is that part of Einstein's equations is relating the round sphere metric to the thing that I would call the shear. And so if lambda were zero, you would have two things. You would have this C being free data and independent, and you would have that QAB would roughly be U independent. So you have kind of all in one, both that the free data is in the subleading shear part of the metric, and that the round sphere metric is static. But the kind of funny thing that happens when lambda is non-zero is that now these are relating the two. So in particular, if I want to have radiation in the flat limit, I need to turn on some time dependence to the boundary metric. And so the radiation is in the cotton tensor. It's in the boundary geometry, which is this funny business. And so that's going to be important, and I guess conceptually, in what follows. But then they even did even more work for us, which is fun because they told us how to go to the Pfefferman-Graham gauge to really compare things. And so there you see that this QAB is in your GAB, and the thing that is the normal 3D stress tensor has in it the Bondi mass, the news, and the angular momentum aspect in a way that is kind of fun in the following sense. So first thing to notice is that it's going to be singular in that flat limit. And so it kind of explains that like Pfefferman-Graham gauge is bad when you're actually in flat. But also it's interesting because then it's like the singular part somehow in that flat limit are what you need for the constraint equations that I need in the flat limit to talk about like BMS symmetry. And so it's nice because it lets you define a 3D analog of a stress tensor, and that conservation will be kind of all you need for the soft graviton story. But in addition to that, you can have some more fun. So this is the first thing I just want to point out is we're going to be taking this flat limit of these quantities. And so the statement I made about the conservation stress tensor was in their paper too. And so all I need right now is kind of just leading behavior. And in particular, there's different ways that I can end up extracting the radiation if I literally wanted to say, well, for these boundary conditions, how would I talk about my flat holograms, like the celestial currents there? I can do whatever I need to do to just extract the news, and that would be enough for me to do it. So that's what I want to keep in mind on the slide for later at the end of the talk if we get to that part. So what do I need? The first thing is we had a limit of the stress tensor because we have J and M, and we know what the stress tensor was in terms of them. And the next thing I need is the cotton tensor, and I also have some explicit form for that. And so with those two, it's enough to evaluate my proposed pointing vector, which was this commutator of cotton and stress tensor. And so what you find is that you start to see the terms in the flat limit, leading kind of singular parts in the flat limit, are exactly the expressions that we wanted to be zero if you had no radiation in flat. So you have the U derivative of the news has to be zero. You have this combination of the U derivative news dotted into the divergence of the news being zero. And then curiously enough, roughly because the leading singular parts of the cotton tensor and the stress tensor are proportional, once you set the U derivative of the news to zero, you see that the next subleading term in the expansion is the next equation that you needed from the PR component of the flat guy. And so basically in the leading flat expansion of this ADS proposal for radiation, plugging into Λ-BMS story, I get exactly the conditions on having radiation flat. So that's great. And that's, yeah. So the issue is I might have an overall sign, but you can check that in the case of the flat limit, this P is time-like. Or yeah. Yeah. So I think, how do I want to say it? I don't know that I have double checked it except for in the flat limit, checking the sign of it. But I think that is one thing to keep in mind, is that like in the Synovia case, the time-like nature of the pointing vector was guaranteed from the normal vector, like various conditions kind of were automatic. Versus for me, I've checked it in the flat limit, and then I would try to ask the authors of the paper if, like, generally for non-zero lambda, if like basically bringing your square plus or square minus, you can see the sign of the, yeah. Yeah. Yeah, see, in the flat limit, it's you get away with it in a fun way. So, yeah, no, but it's kind of cute because as soon as you trust Synovia that P is null, there's a kind of quick way to see that in the flat limit it works out, right? Because roughly the like dudr versus dvdr come with a different sign, and so like the null vector, once you've told me the u component and the a component, the r component signs flip in the two, like if I am modeling that region of the conformal boundary as being in versus out. But presumably the problem is that they can do both. You would say it's open. Yeah.
Is it in or out?
Yeah, I mean, definitely yours works in the leading flat limit. I mean, I still think there's something non-trivial. I mean, I would assume that you would get the sign to flip just from the fact that when you go to the incoming coordinates, the metric is a little bit different in your choice. Like you're building something in there. Yeah, no. So I'm saying that your Λ-BMS gauge is building in that it's leaking outwards when you for that future one. So there's something built in. But I don't know if it's built in beyond the leading term. Right? Okay. But yes. So I know what to do if I want to move a little bit away from flat, but I don't know how to move all the way. But I care about flat. And I care about changing what people do in ADS a little bit. So, okay. So then I guess this slide is just a little bit of a review of the celestial story, because I wanted to set up that eventually I was trying to use it's not just to verify the definition of radiation, but also that for these spacetimes that are radiative, which are different boundary conditions than the ADS that a lot of people would be using, I can extract the celestial symmetry generators in a different way. And so all I basically want to say is, right, Andy was able to take this covariant phase space story near future null infinity, find a reason for us to match it from past null infinity and get a ward identity that could be recognized as a soft theorem. So the thing that I need from this slide is just, okay, so suppose that I have these currents, and effectively it's the fact that like within amplitudes, they're holomorphic, and that's why they're interested, because they're trying to look at this like 2D CFD structure. But so long as you give me the news, I can give you these currents. I can just take you integrals or whatnot. So the celestial kind of has two kind of milestones when it comes to symmetries in this 2D CFT story. The first one is that soft theorems are word identities for these asymptotic symmetries where we know the diffeomorphisms that we're doing and that how they preserve the phase space. And then the second thing that happened is once we had the stress tensor and we changed to a boost basis and we trusted too much maybe, people were looking at collinear limits of scattering, and from the collinear splitting functions, finding a lot more symmetries if you treated it like a radially quantized 2D CFT. So That second step is something that seems quite weird from, like, at least the way that I would always have thought of the way I knew how to see celestial symmetries. And Laurent and friends have really tried to explore how to connect those two pictures better. But for me, again, the thing that I need is that, okay, there are these proposed symmetry generators that I know how to construct in terms of basically I just need to do whatever contour integrals on the celestial sphere to select out these currents that I expect to get when I take my conformal dimension to various integer values. And I can take that conformal dimension to various integer values by smearing in U. And so basically, so long as I have the news near my conformal boundary, I can smear in U with the appropriate near integer weights and get all of the ingredients for these celestial currents if I wanted to from my ADS guy. And so one could do that either from looking at the leading flat limit of the Schouten tensor, or Schouten tensor, and similarly from the stress tensor or from the Cotton tensor up to this funny epsilon tensor that's there. The thing that I wanted to point out is that it's very easy to do this in the sense that, like, but the thing I've cheated at or whatever is that I have different boundary conditions in ADS. And so, for example, there's a quite different proposal by Reclariu that is saying that I can get from a 3D shadow of the stress tensor, probably not changing boundary conditions, but if there's some contact terms that are changing the boundary metric, maybe it's like secretly in there, she can reproduce something that looks like the leading and subleading soft gravitons. And that's just coming from the form of the soft theorem in the form of the 3D stress tensor word identity. Versus for me, the form of the conservation law for that 3D stress tensor is giving me the constraint equations which were underpinning the word identities. But I am not it's not the same formula. And that's because it's different boundary conditions. So I think understanding that connection, because these modes should basically be like symplectically paired with each other or something, or sources of each other, would be worthwhile, because there's kind of two different proposals that are okay because they're different, they're acting on, or they're using different boundary conditions. But the other thing that I think is also kind of fun is from the point of view of, and maybe this is where there'll be some debate saying I can or can't do it, while the authors of the Lambda-BMS paper showed that the conservation of the stress tensor was equivalent to the constraint equations that I would need, the way that it works out is you can see in the flat limit is the flat limit of that conservation law reproduces those constraint equations, but the stress tensor itself doesn't have a good flat limit, roughly because the, if I write it with one index upper, I have a subleading term in the connection that will mix orders in 1 over lambda in the expansion of the stress tensor. So effectively, I can get the right constraint equations, but I am mixing an overleading piece with the piece where I want the sources to be if I had matter. That makes it so that I don't just have a good like flat limit of this 3D stress tensor. And so it'd be interesting to try to play around with maybe adding some torsion or whatnot that you can do when you're not restricting yourself to the covariant derivative that I get from this like flat limit, to see if I can define maybe an intrinsically Carrollian stress tensor, but that is not what I see in this flat limit. So one other fun thing to keep in mind is because this W infinity symmetry story is really, at least naively, just tied to self-dual gravity. When I am self-dual, I have some, I guess, some nice tricks up my sleeve. In some situations, I guess, like you actually have that the Cotton tensor is equal to, up to assign the stress tensor. And so in particular, if you try to subtract off the divergent pieces, you can do so, but you won't have a conserved tensor anymore, but the source kind of goes away when you either have only CZZ or CZ bar Z bar. So it might be fun to kind of look at those. I don't want to use the word renormalize because we already debated that. But like the objects that are well defined in the flat limit wouldn't be conserved. So basically the summary of what I tried to show in this talk is, and how did I do on time? How are we doing on time? I'm also just curious for my own sake of how I did on time. Okay. Okay. So basically in this talk, the point was to try to talk about radiation taking the de Sitter result, going to ADS, and in particular saying that this asymptotic radiation required both the boundary Cotton tensor to be turned on and also the standard stress tensor. And I'd say that there's kind of two parts of the result. One is that it's consistent with the flat limit, so we can understand a little bit about going away from the flat limit. And then we also see a way to extract kind of the news and things that I need to create the celestial currents from that flat limit. But I think there's a lot of things one could do differently or better, and or at least extending them. So the first thing is that a lot of people in the ADS-CFT literature probably are implicitly somewhat changing the boundary conditions when they look at correlation functions in the vacuum. And so to what extent, like, should we understand, like, we're trying to do something that's non-perturbative in G Newton, maybe but perturbative in lambda. You can reproduce scattering amplitudes from flat limits of ADS-CFT in the context where they're probably just zooming in on that bulk point. So I think a little bit of a better understanding of what you can or can't get by deforming the boundary conditions or not. The other thing is this intrinsically Carrollian stress tensor, rather than this object that was different orders in lambda in the flat limit, but reproduced the right conservation laws. And then I'd also say that the analysis we did of the ADS radiation is lacking on the mathematical rigor compared to what Sinavia and friends did in the Sitter case, but it worked for us precisely because we're interested in the flat limit. So that was my talk, and thank you guys.